Hi, today's video involves optimization. We're going to use calculus to find the optimal value under certain circumstances. And I'm going to do some examples. Let's look at examples from that you have worked out. The first example that I'm going to do is number 4 in the worked out section. Again, so you don't have to read as I try and write. And we have a Norman window, which is a rectangle surmounted by a semicircle. And we want to find the largest possible area, dimensions basically, really just the dimension of the base. That'll give us the largest possible area given a constraint and generally speaking, when we have an optimization problem, there is a constraint given that the perimeter is 30 feet. Okay? So, make sure I have my units correct. If I want to find the area, largest area, first I need a formula for the area, and we'll deal with the semicircle first. If I call this R, then the area of a circle is pi r squared, which means that the area of the semicircle is 1/2 pi r squared. Notice if that is R, then that makes the base of the rectangle 2r. I do not need a variable for that. I do need a variable for the length of the rectangle, and so the area of the rectangle part is 2ry. Okay? Now, I want to take the derivative of this, but I need the derivative of a function. This is not a function of a single variable. I need the function of a single variable. You deal with functions of more than one variable in Calc 3. So this is where my constraint, the perimeter being 30 feet, comes into play. This, by the way, is called the optimization equation. What are we trying to optimize? Give me an equation for that. This is called the constraint equation that I'm going to come up with. The constraint equation involves the perimeter. The total perimeter is the perimeter going around the rectangle, which is 2y plus 2r. We don't need this piece in the middle, that's not perimeter, plus the amount of the outside of the semicircle. The circumference, which is the perimeter of a circle, is 2 pi r. Since I have half of that, it would just be plus pi r. And we are told that that is going to be 30. We want the largest possible area, so I'm going to use the largest possible value for the perimeter. So I can then solve this for a variable. I'll solve for y. 2y is equal to 30 minus 2r minus pi r, or y is 30 minus 2r minus pi r divided by 2. If I put that in, substitute, I get my area is 1/2 pi r squared plus 2r times 30 minus 2r minus pi r divided by 2. And notice I now have a function of a single variable, the variable being r. I'll distribute this, 30r minus 2r squared minus pi r squared. The only variable I have now is r, which means that we can now take the derivative. The derivative then is going to be pi r plus 30 minus 4r minus 2 pi r The optimal value, the maximum value, is going to occur where the derivative is 0. And so I will take this. Do not put equals 0 here. You're saying the derivative is always 0. Change the function into an equation. Pi r plus 30 minus 4r minus 2 pi r is equal to 0. That then gives me, solving for r, I get, I'll leave the 30 on this side, and so that gives me pi r plus 4r on this side. These combine and move that. Oops, if I can factor out the r, and we get that r is equal to 30 over pi plus 4 feet, whatever that is in terms of numerical value. You can use a calculator, or you can leave it like this. Use the calculator to get an approximate value. This is the exact value. The question that was originally asked is, what is the base? Notice this is not the final answer because the base was 2r. And so the base is going to be 60 over pi plus 4 feet. Make sure you put units. Do another example, another problem. This is problem number 9, I believe, number 8. In the worked out problems, we have the function y equals the square root of x. This is y equals 0, x equals 9, forming this area, and I want the largest possible, the area of the largest possible rectangle using the x-axis as a base, that it can be put into this particular region. So I need an area. Now, we have to be a little careful here. I do not want to label this distance of the length of the base of the rectangle as x. We are dealing with a coordinate axis. X is the distance from the origin. We want to make it the positive distance in the positive direction from the origin, like it normally would be. So then this point here on that corner is the point xy, which means if this distance is x, the length of the base of the rectangle is 9 minus x. And so my area, my optimization equation, is 9 minus x times y, because this height being y. Now, the reason why I want to do that is if I make x like it normally represents in the coordinate axis, then y can be the function that we're using. Y is just the square root of x. Or I can now write this as 9x to the 1/2 minus, minus x to the 3/2. I wish I could write correctly. 9x to the 1/2 minus x to the 3/2. I change my optimization equation into an optimization function. This is my optimization equation. This was my constraint equation. I use the constraint equation with the optimization equation to get an optimization function. Once I get the optimization function, the next step is take the derivative. The derivative is, in this case, 9/2 x to the negative 1/2 minus 3/2 x to the positive 1/2, or 9 over 2 square roots of x minus 3 square root of x over 2. I then want to find where this derivative is 0, get my critical value, and then I forgot to do something in the first example, so I'm glad I'm doing 2 examples here. We will set this equal to 0. Multiply by 2 square roots of x to everything. This gives me 9 minus 3x is equal to 0. I'm just going to write multiply by 2 square roots of x to everything. That's the common denominator. And so I get x is equal to 3. This is my critical value. I really need to see if this critical value gives me what I'm looking for. It generally will, but we have to show. And for that, I'm going to do my second derivative test. This is what I should have done on the first example. You can go back and do that. The second derivative is going to be negative 9/4 x to the negative 3/2 minus 3/4 x to the negative 1/2. Or negative 9 over 4 square roots of x cubed minus 3 over 4 square roots of x. Notice the square root of any real number besides 0 is going to be positive. So therefore, this piece is negative, this piece is negative, which means it doesn't matter what value I put, but specifically when I put in x equals 3, the second derivative at 3 is negative, concave down, which gives me a max. And so therefore, I get what I'm looking for. I was trying to find the maximum area. I'm still not done with this problem, however. I believe we wanted to find the actual maximum area. The maximum area occurs when x was equal to 3. And so therefore, I will substitute that back into my function, my optimization function. And I get the area being 9 square roots of 3 minus 3, minus the square root of 3 cubed, which is 9 square roots of 3 minus 3 square roots of 3, or 6 square root of 3 square units. That's my unit in this particular case.